Mesdames et messieurs, mesdames et messieurs, chers collègues, chers publics, salam alaikum. C'est avec un grand plaisir que nous sommes présents ici pour évaluer les travaux de recherche de la doctorante El-Heshi Hana. Avant de commencer, je voudrais remercier les membres du jury d'avoir accepté et consacré leur temps et leur expertise à l'évaluation de ce travail de recherche. Le jury qui se trouve aujourd'hui devant vous se compose de le président, professeur Bouba Hossein, Université de Guerna, encadreur, professeur Dar Assab, Université de Guerna, examinateur, professeur Kamel Mesroudi, Université de Sugaras, examinateur Dorman Hakim, maître de conférence, Université de Guerna, et M. Labioud Mohamed Ayman, comme invité, Université de Paris, comme encadreur, et M. Boumahrez Farouk, Université de Abbas Lagharou Khanchla, comme examinateur, comme co-encadreur. Donc, la parole est à vous.
Respected members of the jury, thank you for being here today. Respected members of the jury, thank you for being here today and thank you for giving me the time to evaluate my work. My name is Hannah and I'm here to present to defend my thesis titled Study and Improvement of the Quality of Service of a Video Streaming by the HEVC Codec in Ad Hoc Network. We will start firstly with an introduction and the problematic, the thesis objective, and then we will define some basic notions. We will discuss a comparative analysis of the use protocols, then the NDC and the voice-based solutions, and finally we will conclude with a conclusion. Firstly, what is a VANET? A VANET is a type of mobile ad hoc network where vehicles are equipped with wireless communication devices to form a network on the go. In VANET, vehicles can communicate with other vehicles and with the roadside infrastructure without relying on a central network, which increases the road safety, the traffic management, and also provides healthcare services. Other networks that we can use which enable the V2V and the V2X communication are the satellite and the cellular network, where the former offers wide range, wide area coverage and high-speed connectivity, and the latter ensures the global reach, especially for remote or rural areas with limited infrastructure. The evolution of intelligent transportation system has led to a significant improvements in vehicular ad hoc network, where the reliable transmission of video is crucial for a wide range of applications, including safety, navigation, and in vehicular treatment. However, the vehicular environment characteristic compose some challenges in maintaining high video quality streaming, and issues like packet loss, high latency, and the various network conditions can degrade the overall quality of service and quality of experience of the end users. For that reason, our goal in this work is to improve and evaluate the performance of video streaming in VANET network, outline its benefits and limitations, and also address the challenges faced. To do so, in this work we present three different contributions. The first one was a comparative analysis of the use protocols in streaming video in VANET networks, and the two others are a cross-layer systems that combine source and channel and protocol-based solution to enhance the reliability, the efficiency of the network, and also reduces the latency. In the next few slides, we will define some basic notions about the cross-layer concepts, the transfer protocols, the high-efficiency video code, the multiple description encoding, and the region of interest-based encoding. We will start with the cross-layer concepts. What is a cross-layer system? It is an approach used in network design where different stack layers can collaborate and share information to optimize the overall network performance, enhances the efficiency, and address some specific limitations like enhancing the quality of service and reducing latency. So instead of each layer works independently, a cross-layer system allows them to adapt and interact dynamically, which leads to better performance in various scenarios like streaming video over wireless communication. The following figure represents the OZ model with its 7 layers. Each layer is responsible for a specific task, and non-adjacent layer cannot exchange data directly. The second concepts are the transport protocols, so they are responsible for transmitting data through the network between the end devices, and also they manage the end-to-end communication process. Some of them are guarantee the correct data delivery, and others do not. The following figure represents the TCP/IP model. So in this slide, we present a simple comparison between the well-known transport protocols, the TCP and the UDP. Where the TCP is characterized by its reliability, where it ensures the correct data delivery. It's connection-oriented, where the TCP establishes a connection between the client and the server before serving any data, and it's characterized also by its flow control, where the TCP manages the rate of transmitting data according to the receiver's ability. On the other hand, we have the UDP protocol, which is characterized by its speed because it doesn't offer any data recovery mechanism. It's connectionless because it doesn't establish any connection before sending data, and also it is characterized by its lower overhead compared to the TCP. Another transport protocol is the QUIC, which is for quick UDP internet connection. It is a modern transport protocol designed by Google in 2013 to improve the performance of web applications, especially those related to safety, reliability, and speed. The QUIC protocol was designed as an alternative of the QUIC protocol of the TCP protocol, and it was built on the top of the UDP. These are some benefits of the QUIC protocol. It's characterized by its faster connection establishment, where it uses a one-way handshake compared to the TCP, which uses three-way handshake. It's integrated encryption, where the QUIC protocol uses the TLS technology directly integrated into the protocol. It is characterized also by its stream independence as its seamless mobility. In 2022, and to make the QUIC protocol reliable or suitable for real-time application, a new extension of the QUIC named Enumerable QUIC was designed. So this extension refers to the concept of using the QUIC protocol in a way it doesn't offer the correct data delivery to make it suitable for application like online gaming, voice over IP, live video streaming, and real-time data feeds. Another type of transport protocol are the multi-path transport protocols. They are designed to enable the use of multiple paths simultaneously for the same connection, which allow the data to be split across different paths, which increases the bandwidth capacity, improves the reliability, and reduces the latency. The following figure represents an example of a multi-path connection between a client A and a server B. The multipath QUIC is a new extension designed in 2017, which enable a quick connection to use multiple paths simultaneously in the same connection, which improves the throughput, reduces latency, and also enhances the quality of service. It helps also control issues from path failures or congestion by changing how traffic is directed. The third concept is the high efficiency video codec or the HEVC. So the HEVC encoder is a modern video compression standard designed to reduce the file size while maintaining high video quality. It provides about 50% better compression than the H.264. However, the HEVC requires more computational power for encoding and decoding compared to the H.264. The following figure represents the development of encoding standards for different standardization organization, starting with the H.261 developed in 1990 till the last one, which is the VVC developed in 2018. The fourth concepts is the multiple description coding. So the MDC is a technology used in video and audio transmission to enable, to enhance the reliability and the quality of data delivery through the network. It is based on splitting the source video into multiple descriptions. Each description will be treated separately and send it through the network. The following figure represents a multiple description coding concept. The last concept is the region of interest based encoding. So ROI in video coding refers to the use or refers to a technique where the important parts of a video are encoded using higher quality than the rest of the frames, which make it suitable for a network with limited bandwidth and with applications that require prioritization. The following, these are some applications, so like the virtual reality, video surveillance, video conferencing, and the telemetry application. Now we will discuss the contributions presented in this work, starting with the comparative analysis of the use protocols, and then we will discuss the MDC and the ROI-based solution, which were combined with a modified extension of the MPQuake protocol to facilitate the video transmission. In this work, or in the thesis, we choose the telemedicine application as a use case for study to provide healthcare services in rural and remote areas. So we will start firstly with the comparative analysis of the different extension of the Quake protocol and video streaming in VANET network or in vehicular environment. So to create a realistic scenario for video streaming in vehicular ad hoc network, we developed a framework based on 3 different components. The first one is the SUMO, which models vehicular traffic for realistic scenarios, the Mininet Wi-Fi, which simulates wireless communication to analyze the network traffic and latency, and also the H.265 or the HEVC, which enables the efficient video encoding using the HM and the FFmpeg softwares. The following figure represents our representation of our VANET modeling. These are some simulation parameters used in this work. So the first table represents different path characteristics, starting with the LTE, the 5G, and the satellite link. And the second table represents some parameters of the vehicular environment, like number of vehicles, simulation area, etc. To evaluate the performance of our proposal, we used the PSNI, the SIM, and the VMAF metrics to evaluate the quality of video at the receiver side, and we used the completion time and the received data rates and the packet loss to evaluate the performance of our modified extension of the Quick protocol. So these are some results of the first contribution, which was a comparative analysis of different Quick extensions. So we compared the annual Quick and the MPQuake protocols for video streaming in vehicular ad hoc networks. So our finding shows that the traditional Quick is reliable but has some delays. The annual Quick reduces the latency but may compromise video quality, and the MPQuake offers a balanced solution by leveraging multiple network paths. We suggest the need for an adaptive transport protocol that can adapt with the vehicular network and the challenges they face. The following table represents a simple presentation of the results. So starting with the SIM, the completion time, and the packet loss results. Now we will jump to the second contribution, which is which was based on the MDC solution. So the following figure represents the adaptation scheme for streaming video hybridly over heterogeneous paths. I've split the source chain into multiple blocks to make it easier to understand. So in the first block highlighted in yellow, the source video will be split into 2 different sequences. The first one using the MDC technology. The first one contains the odd sequence, and the other contains the even sequences. Each sequence has lower but acceptable quality, and the reconstruction at the receiver side leads to better to better quality. This technology can enhance the overall data transmission and also the error resilience against by ensuring that successive frames are not affected by the same errors. The second block in orange represent the HEVC or the encoding process, where each sequence will be encoded separately using the HEVC encoder with the same visual quality, which results in an odd and even substreams. Nextly, each substream will be scheduled to be sent through the network separately and in the same time. The last block in red represent our modified extension of the AMPIC-WIC protocol. In this work, our team developed a new extension of the AMPIC-WIC protocol that enable the hybrid data transmission. So the classical AMPIC-WIC sends data reliably through the network, and our extension enable the hybrid data delivery, where it enables the enable and the reliable at the same time transmission. So one sequence will be sent through the network using the enable link, the enable data delivery, and the other using the reliable. After receiving the data at the receiver side, the HEVC decoder will decode each substream separately and before reconstruction at the end. So an error recovery mechanism will compensate for the lost frames by copying them from the even sequence, which was but before the two sequences before getting reconstruction at the last of the transmission chain, the error recovery mechanism will compensate from the frame from the lost frames by copying them from the even sequence, which was received correctly, and reconstruct the output video or the received video. These are the simulation scenarios, so 3 different scenarios was assumed. The first scenario streams videos using the classical AMPIC-WIC, the second using the enable-WIC, and the third one using our proposal. Now we will jump to the obtained results. So the following figure represents the completion time assessment for different scenarios. So the columns in blue represent the AMPIC-WIC performance, in red represent the enable-WIC performance, and the yellow our proposal performances. As it is obvious that the AMPIC-WIC records the highest delays, where it took from 19 to 68 seconds to complete the data transmission. This is due to its data recovery because it transmits any packets, any lost packets. The enable-WIC records the best results in terms of completion time, where it took from 10 to 21 seconds to finish the transmission. This is because it doesn't offer any data recovery mechanism. So on the other hand, our proposal improves the AMPIC-WIC performance, where it took from 10 to 22 seconds to finish the transmission, because it used the enable path, which reduces latency. Now we will discuss the video quality assessment represented in the PSNR. As we already said, that I use 3 different metrics, the PSNR, the SIM, and the VMAP, but I will present only one metric for each contribution to save time. So in this contribution, I present the PSNR values. So as it was expected, that the AMPIC-WIC records the best results in terms of visual quality because it offered the correct data delivery. The enable-WIC records the worst with a PSNR of range from 20 to 25, and our proposal improves the visual quality, the received visual quality by up to 34, a PSNR of 34 okay value. This is due to the reliable because we ensure the correct delivery of the even sequences. The following slide will present the received data rate assessment. So the proposed system achieves up to 143% improvement in receiving data rate compared to the traditional MPIC work maintaining high quality standards. And the following slide will present the packet loss. Okay, I have a typo here. Okay. So the proposed approach reduces the packet loss rate by up to 50% compared to the enable quick, ensuring priority packet are resourced via the reliable links for complete and correct reception. So to summarize, thanks to the combination of the modified MP Quick and the MDC, the proposed approach improves the streaming video quality by up to 70%, according to which resolution has been transmitted, and reduces the network latency by up to 60%. It improves the received data rate by up to 143% and packet loss by up to 50%. Now we will jump to the third contribution, which was a ROI-based solution. So in this contribution, we present a cross-layer system that identifies the ROI regions using two different technologies. The first is the GMM technique, which is a traditional method for identifying moving regions, and the YOLO version 3, which is a CNN model trained specifically on the data video or the video data set. A medical expert group from Henry Mondor University Hospital from France confirmed that the both techniques have almost the same performance, but we use the GMM because it offers significantly faster processing than the YOLO version 3. The following figure will present the compression and the decompression method within the sequence diagram of the proposed system. So as we already said that the source video will be split into two different sequences. The first one contains the ROI frames or the ROI sequences, and the other one contains the background using the GMM technique. Each sequence will be encoded separately using different visual quality. We choose to encode the ROI sequence using higher quality than the background because of its importance, and sacrifice the background quality. Nextly, the ROI and the background will be scheduled to be sent through the network using the modified extension of the MPQuick separately. At the receiver side, a HVC decoder will decode the received substreams, and then the two sequences will be reconstructed or combined to generate the received medical video. The following figure will present the proposed ROI-based streamful multipath video streaming using hybrid data delivery mechanism. As we already said, that the input video will be split into two different sequences using the ROI separation or using the GMM technique. Each one will be encoded using different quality than the other one, and then each sequence will be scheduled to be sent through the network using the multipath extension, the modified extension of the MPQuick. This extension in this contribution differs from the other one used in the first contribution by the priority block, where in this contribution we prioritize the ROI transmission because of its the reliable ROI transmission because of its importance. Now we will see the simulation scenario. So in this contribution, we assume 5 different scenarios. So each one will differ from the other according to the protocol used to send data and also the encoding technique. Now we will discuss the obtained results, starting with the visual quality assessment presented by the VMAF measurement, VMAF values. So the following figure represent the VMAF measurement for each sequences as as it is obvious that they modified Ampeg Wake outperforms the Annabelle Quake by up to 50% in over video quality and by 50% in ROI quality. Also, the reliable transmission of voice, this is due to the reliable transmission of the voice sequences, and the higher compression contribute to improve the performance. To summarize, the simulation results demonstrate that our approach improves upon both state-of-the-art Ampeg Wake and the Annabelle Quake protocols. Specifically, the overall video quality increases by up to 40% with up to 50% improvement in raw regions quality compared to the Annabelle Quake. Additionally, the end-to-end delay or the completion time delays is reduced by up to 35% compared to the Ampeg Wake delays. Furthermore, our modified extension will cause a significant improvement in data rate measurement by up to 86% compared to the classical Ampeg Wake. So to finish, in this work we present 3 different contributions. So 2 different cross-layer system which combines the source and channel and protocol-based solution for streaming video application in VANET network. Enable the hybrid data delivery to send data through the network, ensures the robust video quality under flexion network, and offering better resource optimization by dynamically adapting to VANET challenges. Our performance evaluation demonstrates superior results in realistic vehicular scenarios designed also for diverse and involving vehicular scenarios. Also provided insights for future development in intelligent transportation system. So this is a list of our publications. So we published 2 different articles in 2 different journals. The first one is with an impact factor of 2, and the second one with the impact factor of 4.5, I don't remember. And the 2 others are communication presented here in Galma and Khanchla. So thank you for your attention, and if you have any questions.